This presentation and video have been prepared to explain the difference between anti-collision and zoning, how the systems work, their shortcomings, how to maximise productivity, possible faults and how to minimise them, supervisor systems and what benefits they can give to site, and the options available when dealing with non-tower crane plants such as crawler cranes, mobile cranes, self-erecting mobile cranes, piling rigs, concrete pumps and so on. The screenshots used are from SME ProSite, but the theory should be the same for most systems available on the market today. It's about 18 minutes long, so I suggest you pause it, get yourself a drink and a snack. Select Planter have a large fleet of tower and crawler cranes, plus a comprehensive fleet of other plant, primarily in the UK, Middle East and Australia. We have a full range of luffing and flat-top tower cranes, and in the UK have a large quantity of high-capacity tower cranes capable of lifting up to 66 tonnes. Whilst we cover all types of site, we specialise primarily in tall and complex sites such as the Shard, the Leadenhall Building, Battersea Power Station and the Shell Centre. On multi-crane jobs such as these, sites have to have controls in place to prevent a collision. The primary method of doing this, as suggested in BS 7121 Part 1 and Part 5, is the use of a project-appointed crane coordinator to plan the lifting to avoid a collision and use tools such as crash radios, spotters and anti-collision systems such as those provided by AMCS and SME. BS 7121 states that the anti-collision system is a useful aid to the operator when working on multi-crane sites, but should not be relied on exclusively in place of operator vigilance and a safe system of work. Zoning is used to limit the area in which a hook block can pass. For example, it would prevent the hook block from passing over a road or railway by limiting the slewing or trolleying and luffing motions. Some crane models have this option available in their control systems. Anti-collision is used to prevent two or more cranes from coming into contact with each other's structure or hoist ropes. In both instances, the systems have to be set up by a trained technician. In order to prevent the hook block entering a zone or colliding with another crane, the system needs to control the crane's motions. To do this, it has to know the stopping distance of the crane. Bear in mind it cannot stop instantly. It has to slow down, much like a car. In the case of a crane stopping too quickly, it would put unnecessary stress on the mechanisms, the crane structure, and introduce a swing into the load. The slowdown angle is measured on installation of the anti-collision and zoning system by the technician. They will measure the angle for the crane to slow down from full speed slewing with its maximum permitted load at its maximum radius. The slowdown angle is used to ensure the crane is stopped effectively and safely and is illustrated as the amber zone in the image above. In addition to the slowdown, a buffer zone is added around the whole structure of the crane. This is for safety and it allows for mass deflection, load size and swing. It is possible to reduce the size of the buffer zone in order to improve productivity on site. However, you introduce the risk of the cranes coming into contact with each other's loads or each other's structure, so it has to be carefully managed. The system is constantly monitoring the slew and the trolley or luffing motion of the crane in relation to obstacles, for zoning, or other cranes in anti-collision. So for zoning, when the crane approaches the fixed obstacle, the system compares the current speed to the stopping angle and will intervene by cutting gears until the crane is in first speed. It will then allow the crane to slew in first speed until it reaches the buffer distance from the boundary. It will then cut any motions which would allow it to enter the zone. In other words, the driver can only do safe motions. Most modern systems have a full colour screen which shows the crane in relation to the boundaries and other cranes. It will display the motions being restricted as it approaches another crane or boundary. Let's see an illustration. The arrows in the box on the left illustrate the driver's view on the anti-collision screen. It represents slewing, trolley or luffing, and hoist, though this is rarely used. As the crane slews to the left, the indicator turns amber when the system intervenes to slow the crane down. It turns red when no further motion is permissible. Safe motions are shown in green. It will allow the crane to move away in full speed but only allow limited speed until the crane is out of the slow down zone, as if it lets it accelerate to full speed, it will not be able to stop it in time. Here, when it slews to the boundary, it is only able to do safe movements, so it can luff up and slew right, or a combination of those two movements. It is worth noting that any crane constantly working very close to a boundary will have its speed and hence its productivity limited, so placement of that crane is critical to an effective site. A couple of key points we should consider. The system does not know the size of the load on the hook. The system does not know the deflection of the crane with that load, and the deflection can be significant, especially on tall cranes. The buffer zone is critical as it accounts for the size of the load and the deflection. If the load and/or deflection is larger than the buffer, then there is a possibility of the exclusion zone being breached or a collision. Another key point is that the system does not know the height of the load on the hook, so it could be a beam or a large shutter with long ropes. Because of this, it does not normally allow a hook to pass over any part of the structure of another crane. How anti-collision works. When a crane approaches another crane on site, the system is constantly checking the speed of the crane against the known stopping distance. It will intervene and start slowing down both cranes when the approach zone is entered. Eventually, they will both be restricted to first speed and then stopped when their buffer zones are reached. Again, only safe motions are permitted, so they can slew or trolley and luff away. This illustration demonstrates two cranes slewing towards each other. When the buffer zones meet, both cranes will be speed limited. See the arrows turn amber. In this case, the upper left crane can still luff or trolley, as it would not affect the other machine. Firstly, remember the system does not know the height of the load. So here we have two cranes of the same height. As the left crane slews, its motion is cut. The only safe motion is to luff up and slew around the other crane. Remember, even if the left crane was 50 meters higher than the other crane, the operation would be the same because the hook or load could be at ground level. In certain circumstances, on the Shard for example, where there was a 100-meter height difference between the cranes, it is possible to allow a load to pass over another crane structure by measuring other inputs, such as hook height or the upper hoist limit switch. The system will prevent a load passing over or alongside a counterjib too. There's usually a 3-meter boundary around the structural parts of the crane, where the ropes cannot enter. In addition, remember the approach zone where the speed is limited. So here, as the crane slews round, it is slowed down and stopped as usual. If we slew it slightly out of the way, the left crane can now slew round until the buffer zones meet, where further movement is blocked. The system does know the dimensions of the crane, so it will allow one crane to pass under the structure of another crane's counterjib, as there are no ropes hanging down from it. The illustration shows the jib luffing below the counterjib of a second crane. This would work even if the right-hand crane were much taller. Okay, so now some key points to bear in mind. When two cranes are working close to each other, the speed is limited on both cranes. The size of the slowdown and buffer zone will limit the performance of the cranes. There's a critical point here. Remember, the slowdown is measured on installation. If the technician cannot do it properly or is rushed and a compromise is made, there will be an effect on the crane's performance throughout the project. It's vital to allow enough time for the system to be properly installed and set up. If the buffer zone is too small, there is a potential for a clash, especially if the load is large. With a large load, it needs to be carefully supervised and manipulated by banksmen with taglines. Placing two cranes too close together will limit the performance or even stop them working effectively. Careful placement of loading bays and careful planning of loads is critical to a productive site. Careful placement of loading bays and careful planning of loads is critical to a productive site. If the loads on two cranes are being placed too close together, both cranes will have limited performance. Finally, if the site is very tight and the cranes are very close together, there may not be another choice than to make the system passive. That is, only have visual and audible warnings, and to not cut the motions. If this is the case, the lift must be very carefully managed, with a crane supervisor in permanent attendance. Now some common faults. Cranes in anti-collision communicate with each other via radio link. In many instances, the free channels are used, but in busier towns and cities, these channels are congested with other radio traffic. If the system cannot get a clear signal, it will fail to safe, which will prevent the cranes working effectively. Often the solution is to buy a dedicated frequency from Ofcom. If there's an issue or interference on the radio signal, Ofcom will investigate and resolve the problem. So if the system loses communication with another crane, what does it do? Well, older systems would instantly block out an area equivalent to the full slewing radius of the crane, but newer systems are more effective. Communication is lost. The system then estimates where the crane could move to over the time of the signal loss and expands the exclusion area to match. If communication is restored at any point, full operation recommences, possibly with no effect on operation. Another possible fault would be for a sensor value to change. This would fool the system into thinking the crane was in a different position and could result in a crash. A simple way of checking the system calibration is to set a test point. This is done by picking a fixed point on site, a gate post or a chain store for example, placing the hook above it and then setting a test point on the system. When a check is required, the hook is physically placed in the correct position on site above the chain store or gate post and the driver presses the test on screen. It will then record the result in the system's memory and confirm that the test passed. The driver has a few options on screen, such as night mode, which dims the screen at night, and view settings. They also have access to basic diagnostic data, which can help diagnose faults remotely. They can also use the test points, as we've seen already, and also create working points, which will help guide the driver to return to the same precise location repeatedly. The driver is not usually able to add or change any zones or alter the installation parameters. They may be able to turn the anti-collision system or zoning on or off. This is known as bypassing or shunting the system. This is usually done with a key switch located in the cab or at the base of the crane. When the system is bypassed, there should be a flashing white light clearly visible to those working with the crane. This is to warn them that the crane has no restrictions on working area and the system cannot intervene to stop the crane if it approaches a zone or another crane. It will only give audible and visual warnings on the anti-collision screen to the driver. Bypassing the system should only be done with the approval of the project-appointed person, or sometimes site management, who should be in possession of the key. Appropriate controls must be in place to minimise the risks. Newer systems can be bypassed via the Supervisor system or an app. Both will only allow a trained user with the correct access to bypass anti-collision or zoning. Here we can see a smartphone app being used to turn off zone G1. The driver can still see the zone on their screen, but the green shading shows that the hook can enter the zone. The username of the person doing the bypass will be recorded in the system. Supervisor systems have been available for a number of years and have some very valuable features which improve productivity and safety on site. The latest systems allow quick alterations to be made, such as the addition of an exclusion zone. It can be done in seconds and will appear on the screen in all cranes at the same time. It will also allow zones to be switched on or off. A zone which is switched off will still be displayed on the driver's screen, but they will be able to place the hook block within it. Site drawings can also be uploaded, which will give the driver a full frame of reference. It is also possible to activate and deactivate cranes centrally, such as if a crane is dismantled or out of service, though the latter needs to be very carefully considered and managed. There will be full wind monitoring if wind sensors are fitted. The latest systems have telematics which record crane data, wind data, test points, bypass operations, and zones being enabled, deactivated, added or deleted. Managing other cranes and plant on site. Is it possible to fit a non-tower crane with an anti-collision system? The short answer is yes, but it's not simple. Tower cranes usually either have a fixed position or a restricted envelope of movement on tracks, for example, which can be measured. For other plant, the position could move, and it is currently very difficult to accurately get that location, though this will change with time as GPS systems become more advanced and more competitively priced. If a piece of plant has a fixed position and is on site for a long time, then it may be worth considering installing an anti-collision system, but it will take time. Another easier solution would be to add a temporary zone around the piece of plant using the Supervisor system. The zone can be added on the system either by positioning the hook block of the tower crane to map out the zone and record the positions, or manually plot it on the layout using the mouse, or plot it using coordinates. Some systems it's possible to have a height restricted zone as well. One point to consider in the Supervisor system is levels of access. The system is protected so only a technician can access the initial setup of the site, the cranes and the zones. Below the technician there are more basic levels of access. The most basic is Viewer, who can view and only download reports. In addition, a user can add their own zones, switch them on and switch them off, and an advanced user can delete other users' zones and plus add their own, and with correct training and safeguards could deactivate a crane. And finally, the Supervisor system will allow several different reports to be generated. This includes hours of operation, movement, slewing area, in other words trails showing where the crane has worked over time, and intensity drawings and wind reports amongst others. The data can also be downloaded in CSV format so it can be manipulated to produce site's own reports. Many thanks for listening. We trust you found this presentation informative and useful. Please have a look at our website for other useful information.